Okay, so today's lesson is going to be on making Lewis structures for molecular compounds that have expanded octets. We've already seen incomplete octets, and this is when a central atom does not receive a full set of valence electrons. And for example, we can look at BF3, boron trifluoride. Now we know from our rules, there are some exceptions to the octet rule. Group 1A gets 2, 2A needs 4, and group 3A needs 6. So if we look at our periodic table, boron is in group 3A, so it only needs 6 electrons. So there are 21 plus 6 is, I'm sorry, 21 plus 3 is 24, so this has 24 electrons. So if we were to draw it out, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. All right, so we have 24 electrons, and boron has 2, 4, 6, making it happy. Our expanded octet, this is when a central atom contains more than 8 electrons. And the key there is central atom. All right, so the central atom contains more than 8 electrons, and this is going to happen on our third period and below because we go from the 4s2 to the, so we go from the 4s2 back down to the 3d, so we have a third energy level there, and this is what allows us to expand and do expanded octets. All right, so that D sublevel is allowing atoms to do expanded octets. So we're going to continue with our Vesper theory chart that we've been looking at. All right, and so let's say that we wanted to have 5 things around the central atom. All right, so if we were to have 5 things around the central atom, let me zoom out so we can see. All right, so here are my 5 things, and they are all bonding pairs. 1, 2, 3, 4, 5 bonding pairs. So here's what the atomic structure of a substance would look like if it had 5 bonding pairs. Its structure is trigonal bipyramidal. Now at this point, we're not going to determine different bond angles because bond angles start shifting and changing and get a little confusing, and it's not part of the curriculum, so we're just not even going to go there on expanded octets. But what this is going to look like when you draw it on your paper, we're going to have 5 bonding pairs. Now let's say we were to take one of these bonding pairs away. All right, so I take off a bonding pair. Now I have a lone pair plus I have 1, 2, 3, 4 bonding pairs. So 4 bonding pairs, and a lone pair. There's still five things around the central atom. 4 of them are bonds. 1 of them is a lone pair. This shape is called a seesaw. And when we draw a seesaw, it's going to look something like this on our paper. Let's say I remove another bonding pair. All right, so in this case, I now have 1, 2, 3 bonding pairs, and I have 2 lone pairs. All right, so I have 3 bonding pairs and 2 lone pairs. This has a T shape, and we're going to draw it something like this. And the reason we call it a T shape is because look at it. It legitimately has a T shape. So we have our 3 bonding pairs and then our 2 lone pairs. All right, let's say I remove another bonding pair. At this point, I have 2 bonding pairs, and I have 1, 2, 3 lone pairs. So I have 2 bonding pairs and 3 lone pairs, and this shape is now linear. And so when we draw it on our paper, it'll look something like that, but I do have a linear shape, all right, where I have the 3 bonding pairs around the central atom. I'm sorry, I said bonding. 3 lone pairs around the central atom and 2 bonding pairs. Let's say I have 6 things around the central atom. So here is my structure with 6 things, and all of these 6 are bonding pairs. 1, 2, 3, 4, 5, 6. So I have 6 bonding pairs alone around that central atom. This has the shape that we call octahedral. And when I draw it on my paper, it's going to have the structure something like this. All right, what if I remove a bonding pair? If I remove a bonding pair, I now have 1, 2, 3, 4, 5 bonding pairs, and I have 1 lone pair. So I have 5 bonding pairs and 1 lone pair. And we say that this is square pyramidal. And it's going to look something like this. All right. So I have a square shape. All right. So here's my square shape. Imagine, let me zoom out a little bit here. All right. So you can imagine this is my square. But it is square pyramidal because it also has this bonding pair that comes straight down. All right, which you can't even see this bonding pair when I have it here, but if I flip it, you can see. So if I was to flip this upside down for you, here's my square. But then if I make my connections from the square up to the top, there is the pyramidal shape. All right. Let me remove another bonding pair. At this point, I have 4 bonding pairs and I have 2 lone pairs, one on this side of the atom, and if I flip it over, you can see there's a lone pair on the other side of the atom as well. We call this square planar. And when we draw it, it's going to look something like this. And we call it square planar, and the name square planar comes from its shape. It is a square, and this square all fits within the same plane. All right, so square planar.